Okay, so consider our function f of x equal x plus 5. How do we show that it's onto? Yeah, that's what a permutation is, one-to-one and onto. It's a bijective function. From the set onto itself, and so it's going from the reals onto the reals. So how do we show that it's onto? Guys, remember back that far to set theory and logic? Yeah, remember onto means that everything in your range has a preimage. So we have to let some value be in our range. And so let's do our scratch work then. I'm going to do the scratch work on the board, it's just easier. So if we start with y in the range, we want some x plus 5 to be equal to that y. So solve this for x. Y minus 5. So y minus 5 is the preimage that gets back to y. And so then we're just going to look at f of y minus 5 and plug that in to see that that is going to be our preimage. So let y be in the reals. And consider f of y minus 5. So f of y minus 5 is equal to, plug it into our function. And what's that equal to? Y. Therefore, what do I know? Y minus 5 is a preimage of y in the reals. Thus, f is onto the reals. We good with that? Your one in part D is very similar to that function. It's x plus some constant m. Well, I just gave m a number here. In our case, it was 5. You don't get to choose what it is, but instead of y minus 5, you're going to use y minus m. That make sense? Okay, so that shows that it's onto. How do we show that it's one-to-one? What's our definition of one-to-one? Yeah, each x value goes to only one y value. So when you're proving one-to-one, you're going to let two x values, I don't know, we'll call them a and b. Let a and b be in the reals such that, and then we assume f of a equals to f of b. Well, what is f of a equal to? A plus 5. And what's f of b equal to? B plus 5. If you solve that, what does that tell you? A equals to b. So you assumed that you have two values going to the same y, to show that they have to be the same x. Thus, it follows that f is one-to-one. Starting to come back from set theory? Yeah, it's a while ago. Since f is both one-to-one. Oh, is it not passing? Oh, that's our shortcut from before. I could have used it, but we won't. F is both one-to-one and onto the reals. Follows that f is a permutation of the reals. Does that make sense? Can we do our first, I think it's the first problem for D that does that.
It's D1.
I think that's D1. Yeah. For every integer n, show that it's a permutation. So those are the steps that you're going to mimic for that one. Now, if you look at number 2, they give you something about function composition. How do you show that two functions are equal? Just going to...
F of x equals.
Yeah, you have to show that...
Implies that.
Well, close. Keep them the same. So you have to show that for every x, for all x in the reals, you're going to have f of x has to be equal to g of x. That's how you show two functions are equal.
Yeah.
They have the same effect on every x. So in your case, you're going to have fn composed of fm, and you have to figure out what is that function value going to be. So tell me what fn composed of fm is going to be. Fm is x plus m, right? And Fn is x plus n. So when you do your function composition, you're going to have Fn of x plus m. What does that become when you plug it in? Now, I would submit to you that that is also going to be the same thing as Fn plus m of x. Am I correct? Because this notation says you take this number down here and add it to the x value that you have up there. As soon as you notice that, you're done. That's how you're going to show the two of them are equal. The second part of that, you're showing the inverse. So you're going to write down the formula for each of them to see what the inverse is going to be. It's going to be a similar process to that. On this right here, I want to show that the inverse equals to something on R. So let me show you how to do that. Question. It's leftover, unerased. Yes. So Scott was talking about, I don't know how we were talking about this, but you know, back in the ancient Egyptian time when they were using clay tablets and stuff to write on. Can you imagine being a student back then and you have this clay tablet and you're trying to get stuff out and the teacher comes by and goes, no, that's wrong. He goes, no, sorry, it's a defect in the mud. It came that way. Get better mud, yeah.
Did you hear that someone pointing out that I heard it came from Maya's were actually the first ones to invent zero Indians?
Oh, really?
Yeah.
I didn't know that.
Well, that's what they claimed. I'm not sure how factual it is.
It's hard to tell who has the first, I mean, because you have to date those things. It's not like they put dates on it.
Well, I think they were dating it with their calendar.
Oh, that might help. I don't know.
But-
To discover zero, the number zero.
No,
To write
I
zero.
had a symbol for zero, but that was the Indians.
Yeah, they were saying it was the Indians because they found it on some Indian temple. Okay, so how do you show the inverse is equal to something? You're just going to use it. So you're going to have f composed of f inverse. I'm doing something similar to, similar to part 2. How do you show it's the inverse? So f composed of f inverse of x. Once you figure out the formula, you're just going to write it down. This is going to be f composed of f inverse is going to be x plus 5. Can I do this? Plug it all in all at once for you guys? I got it backwards, didn't I? You plug in f inverse to the original function. But what is that equal to?
X.
Equals to x. And go the other direction. So when you go in the other direction, what do we plug inside? X plus 5. And so that's equal to x.
Star for you.
Thus, what we have, our formula, f inverse of x is equal to x minus 5 on the reals. So that's what I want to see. Once you've calculated what the inverse should be on your scratch work, then just write it down. That makes sense? That's the second part of that proof for number 2. Number 3 is showing that something is a subgroup. How do you prove that something is a subgroup?
Oh, we just did that.
It's closed under the operation and it contains its inverses. Well, you know from number 2 that it's closed under the operation because the operation is function composition. You know from number 2 what the inverses are. So it's essentially apply number 2 and note that it's a subgroup because of number 2. So you've done all the work for number 3 by the time you get to it. You just say by number 2, it's closed under the function composition. It contains all its inverses, therefore it's a subgroup. And number 4 is the only one you have to think about. How do you show that something is cyclic? Yeah, it keeps going around. That means find a generator. If you find a generator for it, you know it's cyclic. So you have to figure out what you would use as your generator. So think about that one for a minute. What would you use for your generator for that? G is our set of functions f sub n of x. And in the integers, yeah. That's close. It's a particular integer. 1. 5 gets you all multiples of 5, but 1 generates everything, because if you add 1, you get 2. Add 1 again, you get 3. Add 1 again, you get 4. So in other words, if you were looking at, let's see what I can use over here. If you're looking at this right here, F1 composed of F1, that's going to be, according to our formula right here, F1 plus 1, but 1 plus 1 is 2. So then F2 composed of F1 is going to be F3. In fact, you can generate them all just by adding 1, doing function composition with F1, because it keeps adding it to itself. So the generator is F1. And as soon as you found the generator, you know it's a cyclic group. Yeah, since 1 is the generator.
For it to be a generator, does it have to get everything?
It has to go to get everything. So how would you get negative numbers from it?
Minus 1.
Yeah, you're going to be subtracting it, doing the inverse of your 1, subtracting the 1.
Wait, so if you have to get everything, how does F1 get everything if it doesn't get the minus 1?
You use the inverse of it. You get to use the inverse of it also. Yes. Yeah. Okay, we are done for today. A few minutes early. Question?
So for number 4, how are we going to prove it? Just it is all 3.
You're not going to prove it. It's really a one-line proof. Because you're going to say, note that this is a generator, therefore the group is cyclic. Yes. Yes.
You don't say
One-line proofs are the hardest ones to think of because you want to do something, but there's nothing to do. Yeah.
I have a question.
What's your question?
You